So we're looking at this, those of you listening at home, John, Jay's, yeah, well, we know Jay's won't watch the video, but John will. So the, what you need to know about motion. So if we go back to the last page we did, which was page 16, should have been, right? And the reason we stopped here is because the first part of this dealt with motion, you know, velocity, position, acceleration, one of the major applications we have. So we need to spend some time with this as we go into our plan. But the first few pages of this packet were about derivatives, using derivative to deal with, and a little bit of antiderivative. We talked a little bit about antiderivative on these. I think the very first page had a problem where they gave you the velocity, and we had to find the total distance traveled. Okay, so let's review that idea real quick. So what we did is very first page, last problem, right? We wanted to know the total distance traveled. So we did the velocity, we set it equal to 0. And so what we did is we found all the places where the particle stopped. So maybe it stopped here, and then it stopped back here, right? And then it came back to here, right? Maybe the particle did something like that. So the particle stopped like twice, let's say, at certain times. So now what that gave us, so here's our x-axis right here, okay? And so what that gave us is the times that it stopped, right? So it gave us 2 time values. Now what did we do with that? We plugged those back into what? Well, the original equation we were given was the velocity. So what do you mean by original equation?
Like
the position. So what we did is did the antiderivative, but it would have a plus c on it. We would know the starting point, so we would plug that in, get our c, and we would know the position function, right? So then we would take the times when it stopped, because that's when it might have turned around, okay? And then we plug those into the position function. Now the mistake people would often make is when they found the position function, they would just, and if we went from say 0 to 6 seconds, they would plug in a 0, plug in a 6, see where it was when it started, where it was when it ended, subtract those. Does that give you total distance traveled? What's that give you? Displacement. So what that would give you would be this distance right here, right? Where it ended, where it started, you subtract those, that's its displacement, not the total distance traveled. So what we said is you got to find out when it stopped. So you set the velocity equal to 0, you plug that into the position, you find out where it was, and then you plug all of that into the position, right? Where it stopped, where it started, and every time it turned around. And then you would just add them up. You'd say, okay, it went this far during that time interval, then it went this far during that time interval, then it went this far, right? Like that. So say it was at 3, then it was at -2, then it was at 7, right? Well, 3 to -2 is 5, and then -2 to 7 is 9, so at 5, then it went 9, that's 14, right? And then we would add that up. Okay, so that's how we did it until we learned about the integral, right? Now that we know about the integral, see if you guys remember this, it's been a while since we talked about it, how do we find total distance traveled? The integral of what? The absolute value of the velocity function. So if we want to know the total distance traveled from 0 to 6, all we have to do is that right there. And it's really slick and easy, especially if we have a calculator. Right? If we have a calculator. Now, if we have no calculator, then this isn't as easy to do. This isn't as easy to do, right? Because now, whatever our velocity is, we probably have to flip all the parts of the graph up, and if we don't have a calculator, it might be hard to graph, right? Now, if it's an easy graph to do, we can do that, right? Something like x squared minus 4, that's parabola shifted down 4, we can flip that up. I mean, we can figure that without a calculator. But when we have a calculator, man, this is the way to go. Totally distracted. So on the next page, on page 21 on, it's going to be more about integrals now. And we can use that new thing we've learned. But we haven't done a lot of problems with it, so this is what we're going to do to practice it. Okay? So let's just run through this real quick, just to review. Velocity is negative and acceleration is positive, then what is speed? Decreasing. If those two are opposite signs, remember, speed and velocity are different, right? Speed and velocity are different. Velocity could be increasing and you could be slowing down, right? Because if your velocity is increasing, if your velocity is negative, you could be going -8 mile an hour, -7 mile an hour, -6 mile an hour, -5 mile an hour, -4 mile an hour, right? Those numbers are doing what? -8, -7, -6, -5, those numbers are increasing. However, your speed is going down, right? You're going slow, okay? So velocity increasing is different than speed increasing. So we got to make sure we understand that, okay? So and we talked a lot about this on that part of the motion packet, actually, is when we talked about this. Okay, if velocity is negative and acceleration is positive, speed is decreasing. If there's velocity and acceleration, you have to look at the two together to talk about speed. Okay? If velocity is positive and speed is decreasing, then acceleration is what? Negative. They got to be opposite, right? If the speed is decreasing. If velocity is positive and decreasing, then what's the speed doing? What'd you have for 3? Okay, think about this. If velocity is positive, so you're going 10 miles an hour, right? But it's decreasing. Well, that's 10, 9, 8, 7, 6. Well, what's happening? You're slowing down, right? So your speed is decreasing. If speed's increasing, acceleration is negative, then velocity is. So if your speed is increasing, so going faster, and your acceleration is negative, that'd be like gravity, then what's your velocity? Got to be negative. Got to be going down, right? When something's going to be going faster when the acceleration is negative, when it's going down, right? When that's happening, okay? And plus, we said velocity and acceleration. If speed's increasing, acceleration and velocity have to have the same sign, so they both have to be negative. If velocity is negative and increasing, then the speed is decreasing. As we were just talking about, if you're going negative 8 miles an hour, negative 7 miles an hour, negative 6 miles an hour, negative 5 miles an hour, that's a negative velocity, but it's increasing. Those numbers are increasing. So it really can get confusing. You know, you talk about velocity increasing, you want it to, in your head, that sounds like you're going faster. Doesn't? That's not true. Okay, velocity increasing. Same thing with acceleration being negative. When acceleration is negative, that sounds to us like it should be decelerating, and that's not true. Okay, if you've got a ball that's dropped, as it's falling, its acceleration is negative, right? Because of the direction. It's the direction that's the positive, negative stuff, right? And that ball is not decelerating. Okay, so that's why I try never to use the word deceleration, right? Okay, because to me that's different. Particles moving to the left and speed is decreasing, then acceleration is positive, because moving to the left means its velocity is what? Velocity is negative, so the speed is decreasing. If it's slowing down and velocity is negative, then acceleration's got to be opposite, got to be positive. Okay, so those are some things to think of. Okay, so let's work for about a half hour or so here, or whatever, we'll see, and then actually, if it takes longer than that, that's fine. But what I want to work on today in here is the rest, basically, of this packet. Okay, now maybe we could, because here's what you're going to have tomorrow. Tomorrow, I'm going to give you a one-sided worksheet that's going to be due on Monday. Okay, one-sided. So it's not going to, I'm sorry, it's one page. It's front and back, but it's not going to take really. Okay, it's about local maximum and stuff like that. Okay, so you're going to have that one page, front and back. That's due on Monday. Then you got the 2015 free response. It's due on Monday. Okay, you got work time the whole day. Okay, so and then I'm also going to hand out to you the sample 5. The sub is the sample 5 packet, but it's only the first section, the 1 through 28, the multiple choice, no calculator, because that's our first test probably we take. So I want to make sure we get some more practice on those no calculator, multiple choice. Now those aren't due on Monday. So you got sample 4, again that's due down the road somewhere, and this sample 5 we do down the road somewhere. So tomorrow you have time, the whole period, to work on 2015 free response, and this one-sided thing is due on Monday. So plenty of time for that. Okay, but if you have some extra time today, you can work on that. But right now, I'd like us to finish this motion packet. Okay, and we'll probably hand that in too at some point, but I'll put that off a bit because we got 2 other things I want to hand it in on Monday, so we will. But we do want to finish this too. So let's work on this for now. And then, like I say, if you got some questions, ask me, because that's part of part of what I want to do, since we're not doing a lot of new stuff anymore, is we've been handing in these packets, and I'm going to hand some back, but what we haven't had a lot of time is time to talk about it. So I want to make sure that we're getting questions answered and asked, about what's going on. Okay, not just copying down answers from an answer book or something, whatever, or from somebody else, right? All right, so let's go ahead and work together if you want on this, and try to finish this up as best we can. Did you ever find it?
Yes, I did.
Out of the way.
I got that worksheet.
Which one? Oh, yeah, so if you're going to be gone tomorrow, I need to give you those. Tuesday. That's gonna be your lead point. That's the one that's gonna be down.